which is close to 20 years. More than 20 years already. So, close to 40 years by Mitchell, when he reported the challenges for the constructions for the Pan Pacific Hotel on Pinnacle and Cavernous Limestone. Of course, now the hotel is known as Surrey Pacific. I'm sure most of us are familiar with that hotel. It's next to the UMNO building in town near Chowkit area. And of course, our good friend, Professor Tan Boon Kong, of course, he gave a lot of lectures with regards to his experience in Malaysia on from a geologist point of view. So in one of his papers, which he had presented in 2004, he also have given some examples of such challenges at interface zone in his paper titled The Practice of Engineering Geology in Malaysia. So, challenges associated with limestone formation. When we're talking about interface zone, unfortunately, because most of the development are in Kuala Lumpur area or even in other city area, for example, Ipoh, ultimately we encounter limestone. And I believe as Malaysian engineers, I think we should be proud that our experience as Malaysian civil engineers or geotechnical engineers, I think our experience in limestone formations, I would say, very good. I think engineers from other countries such as Hong Kong or Singapore, even other parts of the world, regularly invite Malaysian engineers to share their experience in dealing with limestone formation and the experience that we have gained throughout the years, especially in Kuala Lumpur and Ipoh area. So that's why I said that challenges associated with limestone formation have been widely discussed. But the problem is that where limestone interfaces with granite, it further complicates the ground conditions. One of the challenges that have been mentioned by Professor Tan Boon Kong in 2004 is that granite limestone contact zone often produces a deep trench due to differential solutioning of limestone along the contact zone. So this is one of the first message that I want to convey already. You have to be careful. Not just you have different, of course, it's difficult enough, you have different type of formation within the same site, but at the contact zone, often it produces a deep trench because of the different chemical characteristics of these two types of rocks. Okay, this example, again, we are still in introduction. These examples, just to give you a flavor that 40 years ago, these are really the challenge that have been encountered by engineers designing the Pan Pacific Hotel in such interface zone. This is taken from a paper by Mitchell in 1985, which I mentioned earlier. As you can see from here, this dashed line is actually the original outline of the hotel tower. But in the course of carrying out the SI, of course, they have boring, they have Dutch cone, and then subsequent additional SI as well. They have found out that the site is located at the interface zone of limestone and granite again. So you can see from here, this is the approximate edge of the cliff drawn in Mitchell's paper, where roughly he delineates the zone between shallow limestone, which is less than 100 feet, about 30 meters, and deep limestone, which is more than 100 feet. And just to give you an example, the section which he has produced in his paper, section 3, cut across the hotel tower. Of course, at the end of the day, they have to change the hotel tower. As you could imagine, maybe the project would not have been viable if most of the foundation needs to be constructed in very deep limestone area. So they've changed the layout of the hotel tower now with the majority of the tower buildings now in the shallow limestone area, whereas there's still a portion of it in very deep limestone area. So as I was mentioning earlier, section 3 illustrates the problems which encountered the engineers back then, even in 1985. So this is a section, geological section at the section 3.3, roughly at this area. Again, I go back, section 3.3. You can see from here, this is hotel tower. From all the borehole and Dutch cone information, they have interpreted, of course, this is illustrated, the limestone bedrock level. See some of the area here, the limestone, this is in feet, by the way. So you can see that the so-called shallow area at the hotel, easily we are talking about up to 100 to 200, plus 120, and plus 120 is close to 300 feet below ground. These are really the hard area, the deep area. Whereas shallower area, we're talking about, probably talking about close to 100 feet or 30 meters. So as you go further away, of course, there are certain areas even deeper. Okay, this is the challenge that we're talking about, such big difference in terms of the bedrock level at this area. So as part of the design of this, the foundation for these structures, of course, they have carried out some preliminary test pile, trial piles, which they divided in two zones again, just to again give you a flavor on the challenges. Shallow pile they define as less than 30 meter deep with 1.5 meter rock socket into limestone, whereas deep pile is about 75 meter deep. And at the end of the day, they have to adopt the contractor's proposal of using 600 thick and wide width of 2,700 or 2.7 meter barrette pile. So at this zone, you can see this is the final foundation layout after changes were made. So shallow area, they can still maintain ball pile, whereas at the deep area, they have to use barrette piles. And they have to design the structure to span across the zone, the interface zone. So that was the approach adopted by the designer for this particular project at the interface zone. This picture I've taken from Professor Tan's paper in 2004. Again, you can see that this is on the left-hand side where my cursor is moving. This side is underlain by granite formation. And the contour here actually shows the approximate depth of the granite bedrock. So you can see the granite bedrock ranges from 6 to 14 meters. And the limestone, of course, is slightly deeper. But the problem is that, again, the strategy at that point in time is that they avoid building the tower within the contact zone. And I do not know the real reason. Perhaps one day I will have the opportunity to ask Professor Tan, why is there no SI at this particular area? But nevertheless, again, the message is still the same. If you look at the section across the side, the granite can be quite shallow, further away from the interface zone. As it goes closer towards the interface zone, it gets deeper. Whereas the limestone is not that deep, around close to 10 meters. But what they can observe is that they speculate also based on their experience is that at the interface contact zone, likely the bedrock level will be much deeper, as I've shown you earlier for the Pan Pacific Hotel Foundation. So again, these are something that we should be careful whenever we are dealing with foundation works at interface zone. So the overriding message that I wanted to convey to fellow engineers attending today's webinar is that, of course, I'm sure that most of us will do simple test study whenever we start a particular project at the site. And we find out what is the geological formation for the site and what is the prior experience or any previous foundation works nearby that area. So if you realize that particular site is at the geological interface zone, of course, we have to be extra careful on the ground conditions. And for this, I'm afraid it's nothing elegant. I'm not talking in today's presentation, as I mentioned, It's nothing about very sophisticated finite element analysis or very complicated foundation assessment. At the end of the day, the very simple but useful tools that we have is that planning and the scope of subsurface investigation, or SI, is very important, because at the end of the day, only by realizing what are the challenges that we are supposed to overcome or tackle, then only we can devise a solution. Whether the solution is a very elegant and complicated solution or a very simple solution, at the end of the day, we still need SI. Let me show you from my own experience. Just now, just for introduction, is that I just wanted to give credit that, of course, many other engineers and geologists have discussed about it. Whereas myself here, I want to share some of the more recent case history that myself have encountered for my projects. And the intention is to share with you the conditions of the site and how myself tackle the foundation design as such interface zone area. The first case history is for the granite limestone interface zone. Just to let you know, if you want to find out more technical details about this, the issues that I'm discussing in this webinar here, which I've summarized in this webinar, I have also published the findings in a paper titled "Foundation Challenges for High-Rise at Granite Limestone Interface Zone." And this paper was published in the 16th Asian Regional Conference on Soil Mechanics and Geotechnical Engineering in Taipei, 2019. So, of course, I have to give credit to my two co-authors, Saw and Li Ying, which helped me tremendously in the preparation of this paper and also for this particular project. I mentioned earlier, of course, for any particular projects, I think most of us will definitely carry out a simple depth study. So for this particular project, it's actually near, for those who are familiar with KL and PJ area, the project site is actually in Kelana Jaya. So towards the south, of course, is the limestone area. Of course, again, we know Bandar Sunway is mainly in limestone. And the famous Sunway Lagoon is actually an old limestone from mining activities from the lake, which is now, very efficiently redeveloped into a theme park. And of course, I think we all know that Sunway is now a very successful township developed by the Sunway Group. Anyway, this site, at first look, purely from the geological map, of course, the geological map is not a precise map. It just gives us a very broad indication of the geological information of the site. One would expect the site to be predominantly granite. Okay, but predominant granite, and of course, when we talk about granite, we thought we will not be encountering problems such as limestone that we are talking about in typical limestone bedrock. Again, these are illustration taken from other engineers that prepared it. I mean, this one I've taken from Engineer Neo's paper. I think most of us are familiar with it. Of course, when we're talking about limestone, we are worried about overhang, we are worried about floaters, cavities, and etc. And from a paper on the classification of karst by Weltham, of course, he have described the state of the karst based on terminology on the age, or rather based on the terms like juvenile, youthful, or matured. So, for example, he have defined karst characteristics as juvenile karst K1, where you can see there are not much, I would say, defects. I can't think of other words now. The defects, you can see in this case, you don't have much cavities. Of course, in limestone, you will still expect a little bit. So this is quite young, juvenile cast K1. As the cast or limestone gets older, from the description here, talking about youthful cast K2, then you see more and more formation of such, I would say from an engineering point of view, undesirable features. We have buried sinkholes. And then as you go to K3, matured cast, of course, there are even more such undesirable cast features. So in the classification by Weltham, of course, the highest he goes in will be K5, which is the extreme cast. You can see in this case that you have all the features which are undesirable for engineers. You have remnant towers, you have undercut cliff, you have dropout sinkhole, you have reactivated sinkhole, and etc. Of course, K4 is slightly better than K5. So I'm just sharing with you again how geologists will describe what is the conditions of the limestone cast. So if they describe it as cast K1, then maybe you will be you would not be worried too much about all these undesirable features. But if from that study they know that this was a very famous extreme cast K5, then you have to be very careful that you should expect a lot of such extreme and undesirable cavities or undesirable limestone features underneath your site. So for this particular site, myself and of course my company, we were lucky that the client is very appreciative of the need of proper soil investigation information before the commencement of foundation works. In fact, we carry out a preliminary SI. I do not remember what is the numbers of preliminary SI. I think in the region of 10, 20 numbers. So when we first carry out the SI, we already encountered two different types of geological formation at this site. One is granite. Another one is limestone. So naturally, we will be a bit worried. And this site is next to a lake. So when this happened, if I bring you back to the earlier site, initial suspicion was that maybe it's not so much the interface zone, because from the geological map, it looks like it's quite far from the limestone area. We thought maybe the limestone which we have encountered from the borehole, maybe some kind of earthworks that were carried out because it's next to a lake. So maybe there are some dumping of limestone rocks. Who knows, maybe the rocks are used as some sort of pond edge protection. So there may be just boulders being dumped, man-made boulders. So nevertheless, we carry out a second stage of SI, and then we found out there are more and more such occurrences. So from there, we rule out that this is not due to dumping of limestone, but is a natural occurrence at the limestone granite interface. So the client wanted to make sure that we cater for all these uncertainties before the commencement of construction works, because they realize that if you start making changes to the design, or the contractor have to wait for your decisions during construction works, that will actually be more costly. And the contractors also will not be able to give you a very competitive rates for the foundation. So at the end of the day, actually the client encouraged us to carry out these numbers of boreholes. In total, there are 161 numbers of boreholes. And from the results here, we found out that there are some boreholes which are purely granite, some boreholes have limestone and granite, and in fact, there are some other boreholes have mix of different types of rock and limestone. So I'll show here. Basically, I rotate this layout and I've colored it so that you have a better idea on some of the how we zone the problematic areas and the challenging areas. Okay, so when we are designing the foundation, naturally we are very worried, or we pay more attention into the design for the high-rise tower. So these are high-rise. We have Tower A. This is the outline of Tower A. And this is outline of Tower B, whereas in between would be the car park podiums. So from the color coding here, you can see that Tower B is the one that is, I would say, the most challenging. You can see what I've shaded with purple or pink color, depending how you see it on your screen. Basically, these boreholes have both limestone and granite. At the same time, if I have the outline of a blue color, it shows that there are cavities in the limestone. Okay, so this one shows the typical limestone characteristics and being made complicated by the presence of granite. I'll show the bore blocks later, but it's not the entire Tower B. Tower B, certain areas only have granite, the one that I've shaded green, and whereas the one shaded yellow, I have actually other kind of materials, mainly a scan and other rocks plus granite. So same thing with podium. So podium, I don't have that much of a limestone and granite. Mainly I have granite or granite mixed with other type of rock material. Same goes with Tower A. So Tower A and podium area, perhaps from a geotechnical point of view, is more straightforward. What do I mean by it's more straightforward? So this is the simplified borelocks. Let me explain. I will call it the granite zone. What I showed here is that this is typically what my company, when we present the borelocks, the line actually shows the SPTM value in the soil. And whereas the shaded area are the rocks. So you can see from here, basically, before reaching the granite, we have different types of rocks. We have some, mostly are skarn, where the type of very hard rock. But one particular borehole also, we have a little bit of schist before encountering the granite bedrock. But I would say this is quite straightforward in the sense that the granite bedrock is quite consistent at reduced level 25. Original ground is about reduced level 20. So the granite bedrock is at approximately 40 to 50 meters below ground level. So we have some kind of certainties there, and foundation design will be quite straightforward. But the challenge will be at this limestone granite zone, which is at one of the other towers I've shown earlier. So you can see from here, what are the dangers of inadequate SI? You see, for example, if you have a borehole, such as the information given in borehole 33, you would have encountered a very thin layer of limestone. Okay, fine, maybe in design you have disregarded it, you core through it, and then you socket into the granite layers. But then, bear in mind, again, as I've said that I have just extracted some of the sample bore logs where both limestone and granite is encountered. If I go back to this layout, you can see that not all have both limestone and granite. Only certain part of the site have it. So can you imagine if for whatever reason your coring depth is inadequate, or you assume that the geological map is inaccurate and this site is actually limestone site, and your development is only at this particular tower area. And what happened is that you carry out certain bore SI, and your termination criteria perhaps is only 3 meters into limestone. So you may have 1 or 2 boreholes, and both your boreholes actually terminate in limestone. And you will have assumed that your foundation design, you can safely terminate into limestone bedrock. But then after that, when you start doing the works, you may have some boreholes at this area, and then you found out that you actually encountered granite. There will be a lot of uncertainties and delays to the site. So even for this particular case, can you imagine? What we need to do is that we have to have enough information to be very convincing to all the stakeholders that this is actually not limestone bedrock, because only 1 or 2 boreholes have this kind of thick limestone. Others, no limestone, or actually very thin limestone. So you see this here, we have very thick limestone, up to 20 meters. And we have to communicate to the contractor that we have enough information, this is no longer a guesswork, that you have to allow for enough time and provision for coring through such limestone before you socket your foundation into the granite bedrock. Luckily, during the construction, this was quite, it's not widespread. On average, I think, if my memory serves me right, on average, I think the limestone thickness is about 3 meters throughout the entire this particular tower. Again, just to show you some of the, these are all metamorphized rocks that I encountered. For this kind of interface zone, naturally, there are many different types of rock besides the predominant limestone and granite. We have wollastonite, we have pyrite, see, we have some breccia as well. So these are some of the pictures of other rock types for this particular site. So I mentioned briefly when I was explaining the Morlocks information that in view of the large numbers of floaters which vary in thickness and nature, this is floaters. I don't think it is limestone bedrock. So the piles are designed to socket into competent granite bedrock. Because if you terminate the pile toe in limestone floaters, naturally, if I were to illustrate here, can you, because again, if I may go back to the slides here, you can see from the SPTN readings that after the limestone floaters, actually it backs to, it's not hard soil. SPTN is about in the region of, in this case, 18 to 20, it's all less than 20. This one 7 to 14. I apologize, the word a bit small. You have to take my word for it. 7 to 14, and this one you see is about 16 and 15. And this one 10 before you have better materials. So if you are terminating the pile within the floater or limestone floater, of course, it's very difficult to be certain how is the foundation performance. Will it cause excessive differential settlement within the piles? Of course, the strategies that we have taken in this case based on enough SI information is to bore through the floater or molder and socket the piles in granite bedrock. So based on that approach, we have actually carried out preliminary test piles to verify, excuse me, to verify the design parameters. One of the important message that I want to share here is also that with enough SI information, and of course, with a very supportive client that is willing to invest in preliminary test pile, we can actually have more economical design. So you see, for example, in the initial assumptions on the design parameters, of course, we adopted the sharp friction of soil based on 2 times SPTN. And based on our company's experience for bore pile in granite formation, with minimum unconfined human strength of 14 megapascal, we believe we should be able to achieve ultimate sharp friction in granite of 1,500. And because of pile, as you can imagine just now, it will be at least 40 to 50 meter deep, and it has to go through the limestone floater as well. We have limited the end bearing to about 15% of pile working load. So translates to about 4,600 kilonewton per meter square. And of course, the factor of safety for geotechnical, we must achieve a minimum factor of safety of 2. So one of the criteria that we have adopted for all our projects using bore pile is that the competent bedrock is defined by point load test results. Of course, this point load test results is codified systematically, for example, in STM D5731 on how to carry out the test. For us, our definition is that point load test must be carried out on minimum 3 intact rock core samples retrieved during bore pile construction to achieve minimum index strength IS of 3 megapascal. In this case, it's 3 megapascal. I must say that it all depends on site. In this case, we have enough point load tests during the SI as well that we know that when we reach the competent bedrock, a majority of the rock materials will be able to achieve the point load index strength of 3 megapascal. So, in the course of construction of the bore pile, if any of the point load index is less than 3 megapascal, we will adjust the rock socket length to be adjusted based on the equivalent rock socket length, based on a paper, based on the approach which I've summarized with my co-author, Engineer Tan, in 2013. We have presented our experience in a conference in Singapore in 2013. At that time, we devised this mainly for the approach in limestone. That's why the paper title is called Foundation Design and Construction in Limestone Formation, a Malaysian consultant's experience, okay, in 2013. Why I want to share this experience is that eventually, when you look at the results from the maintain load test, the preliminary instrumented maintain load test, you will see the value of why we need to correlate to the index strength when you carry out the bore pile. So to give an sample of the equivalent rock socket length, you can see from here, just now I've mentioned that if the index value, point load index strength is more than 3, we can adopt the maximum, which we believe achievable, of 1,500 kPa ultimate. But what if the rock encounter at site is weathered below, so that the strength is actually below 3 megapascal, which is possible because no rock, no materials, geotechnical materials would be uniform. So, which is why we have adopted, based on our experience, certain downgrading of the friction based on the reduced index strength. For example, if the index strength is between 2 to 3, then it's only 60% of the maximum, which is about 900 kPa. If it's smaller than 2 but bigger than 1, it's only about 40% of the maximum, which is 600 kPa. And if it's less than 1 but more than 0.5, it's only 20%, which is 300 kPa. Of course, if it's less than 0.5, we would deem that as not as a rock socket, but more based on soil. Okay, so this is what was initially adopted for this particular site. Excuse me, I just wet my throat. Excuse me. So, if you look at the instrumented test pile results, we have 2 numbers of preliminary test pile. Of course, we carry out one on a smaller diameter, which is a 900 millimeter diameter, and we have one larger one, 1.8 meter diameter. Smaller one, we are using the conventional cartridge blocks because, of course, the load will be smaller, whereas 1.8, it will be quite challenging, and I don't think it's practical to carry out up to 3 times our working load using the conventional cartridge blocks. So that's why we have used the bidirectional test method. So this is to show you where we have the instrumentation levels for the test piles, and the nearest borehole for this particular test pile, 900 millimeter diameters. So you can see here we have socketed into the granite rock, roughly about, I think, close to about 3 meters. So we have at least 3 numbers of strain gauges and telltale within the rock, and of course we have at least 3 numbers in the soil layer as well. So for the 1.8 meter diameter piles, similarly, of course, you see the nearest borehole shows that the rock is shallower. Of course, during construction, we found that it's slightly deeper at our RL27. So the total rock socket is close to about 4.6 to 5 meters. Of course, we have some instruments below the jack and some instruments within the rock above the jack as well. And then thereafter, these are all the instruments in the soil layer. So this is the results that we obtained from the instrumented test piles. On the left here is the mobilized unit shaft friction in ton per meter square. And this is the pile top settlement. So of course, the L4 and L5 is the deeper level of strain gauges. You can see L4 and L5, of course, the mobilized shaft friction is higher, up to about 90 ton per meter squared or 900 kilonewton per meter square. Whereas you can see for at the soil layer is generally hovering about 10 ton per meter squared or about 100 kilonewton per meter square of shaft friction. This is the mobilized shaft friction for T900 tested using conventional cartridge system. And you can see the end bearing. Of course, you can see the end bearing, it requires quite large, initially not much mobilized. Of course, when the friction all has been taken up, you can see they start to mobilize. But as expected, the mobilization of the end bearing requires quite large movement, okay, of the pile bottom. You can see here, so it can mobilize quite high, about 3,000, but then again, the pile bottom need to move about 35 millimeters. Again, this is expected, and that is why it's very important that the geotechnical design, anyway, from my experience anyway, that sometimes you will see in certain projects, the base may be very good, whereas from other side, the base may not be very good. But that are the challenges because different contractors have different approach in terms of constructing the bore piles. Some may have used very deep casing, some may be using very shallow casing, and then relies on the bentonite, on the polymer to stabilize their bore hole. So again, testing will give us very good indication on the performance of the piles and how well the base cleaning will carry out. So, whereas for the 1.8 meter diameter bore pile, again, this is a result similar. Left-hand side will be the mobilized unit shaft friction. And here a bit different will be the hydraulic jack displacement. Of course, we have two sets of results. One will be the segment above the hydraulic jack. The other one I'll share later on will be the segment below the hydraulic jack. So again, you can see these two upper curves. These are basically for the lower level of the strain gauges at the rock level. You can see that it can mobilize quite high. Again, it goes up to about 1,300 kilonewton per meter square, whereas at the soil layer is lower. It did not exceed 200 kilonewton per meter square for the soil layer. And similar results, I would say quite similar for the segment below the hydraulic jack during the third loading. Why I've shared the third loading? Because this will be the maximum values which can be obtained. You can see again, for the maximum rock shaft friction, it can be mobilized at fairly smaller, relatively smaller pile movement or jack displacement in this case. So about less than 10 mm, we more or less mobilize the maximum value of the rock shaft friction. Whereas again, you can see in this case slightly better in terms of the end bearing. In this case, the end bearing can mobilize quite large value of up to 7,000. Again, I would say fairly good in this case. Less than 20 millimeters, you've already mobilized more than 6,000 and close to 7,000 kilonewton per meter square of end bearing. So at first look, when we look at the results, when we compare the design assumption or ultimate shaft friction, you look at it, the design is about 2N, whereas for TP900, on average, the shaft friction looks higher, about 5N, whereas for TP 1.8 meter diameter, TP1800 is lower, 1.5N. What we observe also is that the ultimate shaft friction of TP900 is about 2.5 times of the design parameter, we observed that there's a slight pile bulging on top portion of the test pile, which may have contributed to the exceptional high value of shaft friction. I mean, this is some of the observations we can see from the concreting records and also observations during the construction of piles. And then we look at the average ultimate shaft friction in rock. If you recall earlier, and of course I've shown here again, that the initial assumptions on the design is 1,500, whereas from the prelim test pile result for both of them, it shows it's lower than their design assumptions. And also the ultimate end bearing, you can see that TP 900 is lower, whereas TP 1800, not too bad, it's better. But on first look, you would think that probably we will be a bit worried in the sense that we were to lengthen the rock socket, because naturally the test pile result shows that the friction that's achieved is lower than the design assumptions. But my conclusion here is that overall, both the instrumental test pile results showed that the design parameters assumed during design well represented the ground condition when adjusted based on site-obtained IS values. What do I mean by that? Let me share with you this particular table again. If you recall earlier, I've mentioned that 1,500 is with the condition where the IS value have to be equals or more than 3. Anything less than 3, based on our experience, we have to adjust the equivalent rock socket. That means we have to increase the rock socket based on lower rock friction. So it's a reduction of up to equivalently 60% if you have between 2 to 3, and 40% between 1 to 2, and only 20% of the ultimate if it's between 0.5 to 1. For me, this is logical, because if you have, for example, if you have very high IS value more than 3, and you have certain zone during construction of bore pile, we have very low IS value. Naturally, you don't expect the rock friction to be the same, which is 1,500. It has to be lower, because when you have such low IS value, means the rock likely have been weathered to a weaker state compared to IS more than 3. And I will attempt to explain to you from this table. So you can see from here, first point you can see is that both these test pile did not fail. That means it achieved up to 270% of the working load for test pile TP900, and test pile 1800 we achieved up to 230% of the working load. That means both these pile definitely can take loads above 2 times the working load. From the instrumentation, what we gather is that the shaft friction, the average shaft friction that we get from the instrumentation is about 897 kPa. If you look at the ratio between the average shaft friction and what would be the equivalent rock socket length, it has to be about 0.6, because simple arithmetic, 897 divided by 1.5, you will get 0.6. So these are the actual index strength value that we obtained from site during the construction of the test pile. For the first layer 4 to 5, actually the average IS value is only 1.418, whereas layer 6, 5 to 6 is 3.517. If I average out the IS value for this, based on these two results, the average would be about 0.7. That is why you can see when we carry out the actual construction of this test pile, we have actually lengthened the pile based on this factor of 0.7. That's why at the end of the day, it is more or less in line with our expectation. Whereas for TP 1800, the rock is much better. You can see the IS value, in fact, is more than 3 of them. And if you calculate the equivalent rock socket length, it will be based on 1360, 1321, 1358. The average actual equivalent socket length will be in the region of about 0.9, as opposed to the calculated one of 1. So in this case, the difference is only in the region of 10%. So the impact in terms of the rock socket is not that big. And because of the end-bearing values, we are still within the margins for the factor of safety. So you can see that the proposed equivalent rock socket length actually works well, because even when we construct the piles, we do not rely assuming a fixed socket length based on the maximum value. We actually adjust it based on what we encounter at site, and that is why the pile test, the test pile results fulfill the criteria and pass a minimum of 2 times the pile working load. So it works. So for this first case history, you can see that one of the important messages that I want to share with you is that at Kuala Lumpur limestone granite interface, we encountered limestone floaters with irregular thickness. And this one actually, to me, we need a very simple, but this tool has been readily available to all engineers for a very long time already. So we have to have adequate rock pouring depth and enough SI during soil or ground investigation. Okay, for this particular site, we have decided to adopt wall pile foundation system and to socket into granite bedrock. And the instrumented test pile results match well with the assumed design parameters. And in this case, we see the benefit of having some kind of monitoring during the construction, adjustment during the construction based on site obtained IS value. And from this particular site, we feel that it is actually a very effective approach in terms of verifying our rock socket in granite. This was the conclusion for case history 1. For case history 2, slightly different. In this case, the interface is at the granite and Kenny Hill interface zone. Sorry, before we continue, let me just again have a quick water break. Okay, excuse me. So for case history 2, we have granite and Kenny Hill interface zone. Just now I've discussed at length about granite and limestone, and I will share with you earlier on also. It seems a lot of the publications in Malaysia that I have encountered, based on my limited experience anyway, most of the experience are mainly in granite and limestone interface zone. So I believe this particular site is quite unique in the sense that it's between granite and Kenny Hill interface zone. And what are the challenges from this particular site, which again I will share with you. I hope you learn something from my experience. So this site is near the Matrade building. Okay, Matrade building, I think, again, for all of us who are based in KL, or those from KL will be familiar with it. I mean, not far from the Masjid Wilayah and Jalan Duta area. This is the particular site near Matrade. So when we superimpose the site location, of course, when we were doing this project, we were very worried whether it will be make more even complicated that it may be interfacing with Kuala Lumpur limestone and granite and Kenny Hill formation. I mean, that would be a quite unique challenge where we instead have 2 different interfaces, we have 3 different interfaces. But I would say, fortunately, in this site, we only encounter granite Kenny Hill formation. Of course, fortunate for the project and in terms of the smooth implementation of it, but it's unfortunate in the sense that I mean, for those who are really thirsty for knowledge, I mean, of course, some of you may look forward to 3 different types of interface zone, but fortunately for us, we don't have that kind of problem here. But believe me, granite and Kenny Hill formation itself is already at the interface already complicated enough. So this site, not a very big site, the ground elevation, you can see from the contour itself, you can see that there are big difference in the elevation. The highest ground is about 75. The lowest ground is about 50. And the final excavation level is about 37.5 meters. This particular site requires a very deep basement. You can see that if you're talking about from 71 to 37 meters, we will need about more than 30 meters deep of a basement excavation. One very interesting features that I wanted to share with you is that you can see from the contour here that this area is quite hilly and steep slope, whereas here lower and gentler area. So at first, one would have guessed that maybe there are some previous earthworks being done over there, but actually it matches well with the area where there is a distinct change in terms of the ground condition between this zone and this zone, which is separated by an existing road. So I think the previous development around the area, they already encountered some kind of issues around this area. Maybe because of that, they decided not to pursue with construction at this area. Anyway, that is purely my speculation. So as I mentioned earlier, based on the contour, and from here, when we carry out the preliminary SI, you can see that there are already existing boreholes at the site. When we already involved this project, we can study from these three numbers of boreholes. These three number of boreholes already show a very clear-cut difference in terms of the ground conditions across this site, in the sense that on the right-hand side here is mainly Canny Hill Formation. On the left-hand side here is Granite Formation. And of course, after that, even during, we'll call it that preliminary foundation design, we carry out additional borehole just to confirm the existing information. And true enough, it confirms that there's a very distinct difference between the ground conditions at the left-hand side, which is Granite Formation, and the Canny Hill Formation on the right-hand side. So again, I summarized, there are three numbers of existing boreholes by others in the 2008, many years back. And in 2016, when GNP is involved, myself is involved in this particular project, even at the preliminary stage, we carry out 12 additional boreholes to verify what is an overview of ground conditions of this site. So from the boreholes that we have carried out, similarly, these are how we summarize the information in the bore logs. On the left-hand side is some of the sample bore logs from in Granite Formation, and on the right-hand side is on Canny Hill Formation. So just to give you a taste of a very obvious difference is that in the granite area, you can see that we would, let's look at this borehole, for example. Basically, you have encountered soil which are gradually, the SPTN values gradually increases with depth. So you have SPTN about 10 to 20, increases to about 30. Then you have this weathered layer where the SPTN is more than 50. I think most of the boreholes encounter this layer where the SPTN is more than 50 before it encounters the granite at this particular layer. This is typically at the, I call that the granite zone. Whereas at the Canny Hill Formation area, of course, we will have some of them are very weathered rock, but very hard material. The SPTN basically is already more than 200. And when they did encounter the rock, whether it's applied or sandstone, you can see that the RQD is actually very low. Most of these kind of materials are associated with very low RQD. RQD is close to 0 for most of the materials encountered. But before that, they already encountered very hard materials at shallow depth. I'll take some bore logs, a bigger view of it, just again to show you the difference side by side. You can see from here, what is the first thing that we can see is that you see these two boreholes, the sample borehole 3 and 8, you can see the hard layer, we don't start to encounter SPTN more than 50. At a deeper layer, in this case, borehole 8 is about 28 meters below ground level. SPTN more than 50, 28 to 36 meters. I mean, not too bad. These are common variations that we will encounter. Whereas you can see from at the Kenny Hill site, of course, as I mentioned, some of the area, the existing ground is lower. You can see some of the boreholes immediately. After 1.5 meter, you really have SPTN more than 50. In fact, most of it are more than 200. So some is only even deeper, is only 5.2. So Kenny Hill site basically very shallow hard layers, and it continues all the way until you have very low RQD values. Whereas granite, you have soil, hard layer before you encounter the granite bedrock. So of course we have weathered rock. We have certain deeper weathered granite layer level as well. So once the development layout are more finalized, where we know where are the major towers, where the building will be sited on to this site. Of course, we have a more comprehensive SI. This is where we carry out detailed SI with the intention of having more information so that we can have more optimum information for optimum foundation design. And also, we wanted to have a better strategy on how we deal with the interface zone. So I have color-coded the borehole information here is that basically the red are very obvious, showing the characteristics which I define it as the granite area, whereas the blue boreholes are the one that are, I would call the Kenny Hill information. The yellow, basically this zone, yellow and certain red and blue are at the interface zone. Why I call it interface is that it's neither the granite or the Kenny Hill features. Let me give you an example again. What are the challenges that we encountered? What I did is that I extracted the boreholes for these three numbers at the interface zone to show you that how we wanted to study it and how we devise a solution for this particular area. So, sorry, how do I hide? Anyway, I hope you can see the full PowerPoint screen. Anyway, you can see on the left-hand side, what we term as the granite zone. We have the hard layer or weathered rock at a deeper depth. Okay, we're talking about, you can see from here, reduce level 20 to reduce level 15. And after that, they have a zone of, you see from here, this, if I may go back, the difference between at the interface zone, the granite layer is that at the pure granite area, you don't have thick, very hard materials. You usually have some weathered material, then you reach the granite bedrock. Whereas at the interface zone, they have some features of the Kenny Hill formation. You see you have the hard layers, then you have very good SPTN more than 200 kind of materials, SPTN more than 200 before you encounter granite bedrock. So of course, in this zone, it will be too conservative for us to ignore all these materials and just assume it's granite. Whereas at the Kenny Hill area, it will be too conservative to ignore all this kind of good material, hard layer or weathered rock, which we encounter at quite shallow depth, all the way to the sandstone. So you see from here, we encounter it, let's say about reduced level 48 to about reduced level, let's say for simplicity, about 15. 50, let's say 50 to 15. We have 35 meters of very good materials at the Kenny Hill area, not so good materials at the granite zone. So we are facing with this dilemma on, but at the same time, we have to juggle between optimum design, but at the same time, we must make sure that it's safe. Can you imagine if we assume that it is at the Kenny Hill zone, but whereas the soil, the pile when you're constructing is at the granite zone. So your pile may have stopped. If you assume Kenny Hill, the pile will have stopped within this zone. But the capacity may not have been enough. The actual zone that you have encountered at the interface is closer to this rather than this. again, these are the challenges that at the interface zone that we have to deal with, because of very obvious change in the characteristics at the interface zone. Just to share with you, because again, this is a very nice project to be involved in, because there are a lot of basement excavation, of course, coupled with the challenges of the ground conditions. Of course, this site, we adopted the diaphragm wall for the basement excavation. I think most of you are familiar with the construction of diaphragm wall. These are the lowering of the diaphragm wall cage. We're using the ground anchors for the some section using ground anchors for the basement excavation, and certain areas to further improve the performance of the retaining wall, because we have to control the movement of the diaphragm wall. The diaphragm wall actually coupled with the buttress. I'll be sharing some experience from this project site in another seminar. This one is organized by IEM Sabah together with MGS as well next week. So that one I will share more on the experience on this, on the retaining wall system. Again, you see construction of the ball piles. Of course, the diameter of ball piles, some of them we have to utilize very big diameter ball pile, 2.5 meter diameter. See, they have lowered down to a certain depth before they start the construction of the ball piles. Of course, the other system as well, temporary steel struts, very interesting project site. But for today's purposes, for today's presentation purposes, I'll focus just on the foundation design. So, what we have done is that based on the interface zone, I mentioned earlier the foundation design that we are adopting ranges from as small as 750 meter diameter ball piles to 2.5 meter diameter ball piles, and we have used grade 40 concrete for the ball piles. And the value of the additional SI, I mean, even though the solution, again, as I said, is nothing really elegant, is that we will be able to confidently delineate where is the zone where the piles we design is based on Kenny Hill formation, and where are the zone that we will be carrying out, assuming the top part there would be granite formation. Because in this case, we err on the safer side. The granite formation, the soil is weaker. So we have to assume based on that kind of information on the top part. So again, similar to the case history number 1, we are fortunate that we have enough information, SI information. At the same time, we actually carry out the prelim test pile in advance. So you can see we are carrying out the ball pile, the prelim test pile 1.2, 1.8, and 2 meter diameter. The main difference is that for 1.2 meter diameter, we carry out in Kenny Hill formation. In fact, there are 16 meter of the bonded depth, because if you recall, I mentioned earlier that there will be basement. Of course, we are interested to test the actual performance of the soil or the sharp friction at the area where below the pile cutoff level. So we have 60 meter debonded, and we are carrying out the cartilage on this particular pile. Whereas these two other piles, we focus mainly on granite formation. One is at the weaker, so-called weaker and longer piles, which is up to about 65 meter in soil, and very nominal rock socket, PTP2, in the northern part here, where the soil tends to be weaker. So the main idea here is to verify the soil frictional parameters, which in this case is quite important, because as you can imagine, the pile is quite long before encountering the granite bedrock. So because it's a big pile diameter, we are using bidirectional. And we have another bigger, even bigger pile, 2 meter diameter. In this case, the granite is shallower. So we have pile length about 46.4 meter. And thereafter, we have 5.7 meter of rock socket. So to give you a picture, of course, I believe this cartilage stack, we need to have a lot of precautions have to be carried out properly. It's quite a high stack, because I think this is more or less the maximum practical weight that we can carry out, or the load that we can mobilize using cartilage method. So these are a view of the instruments that we have installed into the reinforcement cage. So let's look at the test pile results. When we're looking at the first pile in Canny Hill Formation, 1.2 meter diameter. So why it's very important that we debond this level, as I've shown you earlier, this is the pile top. The nearest borehole is this particular borehole. For this Canny Hill Formation, all this material actually very good. So if you don't debond it, actually we will not be able to test. A lot of the load probably will be taken at the top part of the soil, and we won't be able to test the lower materials which are on the level which we are interested at. So this is below the cutoff level. So we debond it, total pile length is about 40 meters, but we debond about 16 meters. So of course we instrument it. So you see from the SI, it shows that it's supposed to have some sort of a fractured, very fractured rock, mostly with RQD less than, RQD about 0. So from the results that we obtain, you can see from here is that again, of course, the higher level will be the lower level and all those better materials. You can see that in fact, I would say these are closer to weathered rock materials, rock-like materials. All these are SPTN more than 400. So the friction mobilized ranges from 340 to about 500. For this, I think we interpreted it as outlier, even though this is still within a very good material, because this level of instruments is close to the bonded area. So we believe this has been disturbed. That's why we don't believe such good materials only mobilize so low, 150 kPa of skin friction. So we disregarded this result. And if you look at the end bearing reaches maximum about 400 kPa. Nothing really great, but it is within expectation. So you can see from the instrumented test pile result, in the soil, I mean, none of the material here would be able to have any point load index strength. That's why we term it as soil, even though it's considered as very hard soil. The FS limit ranges from 150 to 500 kPa, whereas for the end bearing is about 400 kPa. Again, what we do is that we do a comparison between the design parameter. Of course, in this case, for soil, we're talking about 2N. This is not very critical. We still maintain as 2N because if you recall, just now I mentioned earlier, there are not many soil materials which are very weak at this material. So the one that is governing would be the ultimate friction limit. From literatures, we're talking about in soil, normally we're talking about limit to 150, 200. So when we talk about design, initially we have assumed it as 250 kPa, which is not too bad if you look at the results. We're talking about 250, you can see here, even very good materials, it ranges from 350 to 400. So in this case, based on the result, we think we can optimize it to the limit of 350 kPa. If it's wrong, I think we make a judgment that it should be able to go for more than 700, about 700 kPa if we have some kind of materials that are more than 3 MPa. I mean, to cater for any uncertainties. And to cater for any possibility at site. But at the end of the day, I don't remember actually we encounter any IS that is more than 3 MPa for this material anyway. Anyway, so that's why this one is not governing. At the end of the day, the design is mainly governed by the limit of soil of 350 kPa. And the end bearing, we don't adopt it because the results have shown that actually it's very small. And it's not much benefit. And what the implication is that from this test result, we can see that we can reduce the pile length by about 30% based on the initial assumptions by 30%. And end bearing ignore due to the following reason. First of all, the effect is not significant. Based on 400 kPa, we found out that the 1.2 meter diameter only reduced total pile length of about 0.23 meter because the friction is very good. So end bearing, we don't need it a lot also. And for most of us who are familiar with Canny Hill, we knew that it's very sensitive in this kind of formation is that the material softens upon contact with water. That's why some of you may know that certain engineers actually have very strict criteria in terms of the time given for opening up the borehole and for the concrete to be poured into the borehole. The main thing is that there are a lot of literatures that say that this Kenny Hill information, both the skin friction and the end bearing, will soften with time. So that's why in this kind of situation, I think it's very prudent, and in fact, the effect is not significant. The risk is not worth it to consider the end bearing in Kenny Hill formation. Next, we look at prelim test pile number 2 and 3, which is mainly in granite formation. Again, just to give you a flavor, an idea on what are the information, borehole information on test pile. This one, as you recall, is mainly in soil material, but nevertheless, we have some very good soil material as well, depending on which borehole that you're referring to. Both of these are quite near. This one, we stop it at shallow depth, but after that, we believe we have weathered materials, SPTN more than 200, and then we have a little bit of rock socket to a rock. Total pile length here is about 65.4 meters. So, again, as we have normally we present for bidirectional test result, you can see that, of course, in the soil, the mobilized capacity will be lower. Whereas you can see from here, the mobilized capacity below the jack, you can see it go much higher because we have the end bearing contribution. So what would be will be interested would be, you can see from here again, even for within the soil area from level 1 to level 3, we can see that within SPTN 30 to even 100, the mobilized friction is only limit to about 100 kPa, 66 to 100. Whereas at the weathered granite, you can recall the SPTN is definitely more than 50. Even that, we are only limited to about 200. Similarly, below it, it's not more than 200, even for the FS below the jack. For the base, you can see that, of course, it can be quite high, but I think important to note, you can see from here that the base displacement actually quite significant before it can actually mobilize the base of 11,000. So in this case, total movement already about more than 60 millimeters, closer to more than 70 millimeters already. So from the interpretation of the result, we can see that in soil, the correlation with SPTN, the K value ranges from 1 to 7. Of course, it's quite normal that it varies quite big range from 1 to 7. And the soil limit is based on quite established literatures, about 100 to 180 kPa. As I mentioned earlier, a lot of publications say that the limit in soil normally is about 150 to 200. So, of course, in granite, we don't have enough rock socket to verify the friction. But the FB limit, of course, just for simplicity, we showed here, it's about 11,000 kPa despite a large movement. So, this is where the value of the second instrumental test piles will be able to give us more information. Again, just to summarize, what are the soil information? Of course, we have typical SPTN on average 20, 125, 200 before we socket into rock. In this case, we have about 5.7 meters of rock socketed. So you can see the pile mobilized capacity again below the jack, of course, is higher because we have the contribution of the end bearing. But what we'll be interested would be here the main thing is that we wanted to again study what is the soil. In this case, we have the main purpose to study what is the friction of the granite rock. So you can see from here again, from the soil, let's start from the soil first, SPTN 1020, again, you can see that it ranges from 36. Even with SPTN very high of 200, it is about 176. Whereas when we're talking about at the two granite layers, where actual construction, we get about 0.8, we get the friction, the point load index 0.8, we get friction about 500. Whereas this one slightly higher, 1, we get about 1,100 kPa in a deeper layer. So for this even deeper below the jack, when we get the point index of more than 3, we actually get the friction of 1,500, slightly more than 1,500. And the end bearing, I say, more or less in line with the previous ultimate value, close to 11,000. But this one is better in the sense that much lesser movement of the pile toe. So again, just to summarize, you can see that again, the K value correlates to SPT N value for the friction ranges 1 to 5. And the limit, again, is broadly in line with a lot of other researchers that we generally, maximum, it won't go above 200 in soil. In our case, about 176. The limit then is 7 to 176, depending on the strength of the soil. And the granite rock friction from our test result ranges from 500 to 1,500 kPa. And we find that there are some correlations with respect to the point load index strength that we obtain during a pile construction. And the limit of the end bearing is about 11,000 kPa. So you can see that even though end bearing for PTP 1,800 can mobilize up to 11,000, however, displacement is very large, which exceeds the allowable limit of 12.5 millimeter under service load, as compared to PTP 2,000. So again, here, that's why I mentioned that end bearing, it relies a lot on workmanship. That's why sometimes certain designers have bad experience in terms of getting the desired end bearing values. My guess is that if you recall, 1.8 meter diameter, the soil conditions is not as good as the 2 meter diameter piles, and this is deeper. So naturally, the potential of disturbance at the toe, and it's of course more difficult to clean the toe at deeper depth as opposed to a shallower pile, contributes to a certain extent on this kind of behavior. I believe there's some accumulation of soil at the toe there, which leads to this kind of result. You can see that after it compress the soil materials, then it reverts back to the expected behavior of the end bearing of the granite rock. Again, as a comparison between the initial design assumptions, so of course we assume the soil friction during the design of 2N will remain as 2N based on the instrumented test file results, and the limit in soil will be based on 150 kPa. From the result, I think we also remain as 150 kPa. I think the instrumented test file results more or less confirm the parameters for the soil. Of course, for rock, we do not have terms of the maximum, but what we are interested to find out would be whether 1,500 can be achieved, which from the test file results, we found that it can be achieved. But the difference is that we found that based on the actual IS value that we obtained from the instrumented test file and correlates the results, we don't have to reduce it so much based on the IS value. Initially, we based on reduction of 60%, 40%, and 20%. But from the instrumented test file result, we feel that we will be able to justify using a higher ratio. That means instead, for example, if we have IS between 2 to 3, instead of using 900, we can use 1,200, which is only a reduction of 20% or 80% of the maximum value. And of course, the end bearing, I've explained it previously. Before we verify the contractor's workmanship, of course, we err on the safe side. We use the ultimate end bearing about 3,000 kPa. And based on test file results, even for the situation where we find that there are some materials accumulated at the toe there, I think 6,000 kPa, when we work backwards with the factor of safety of 3, the movement to mobilize this ultimate end bearing can be achieved. That's why we have upgraded the end bearing in the granite and also the friction values. Of course, at the end of the day, with this, the reduction of piling in rock, which is a major cost component, is about 30%. So in summary, just to give you an example, so original design, for example, the piling in soil may be 24 meters. Based on the instrumented test file result, we can actually reduce the pile length from 24 to 17.5 meters, which is a reduction of 6.5. This contributes to 27% reduction of pile length. And whereas in granite, when we optimize the rock socket, actually the rock socket reduction is about 0.9 meters, which translates to be about 30% the reduction of rock socket. So again, these are the benefits of the prelim test piles. I think when we translate to the entire site, the cost for the prelim test pile definitely far less compared to the savings from the actual production piles. Next, I want to share with you that, remember we're talking about the interface zone. Despite we already determine where is the interface zone. To ease the contractor, of course, we have to have this kind of scenario to the contractor. Even for all the different areas, for example, at the Canny Hill Formation, we give them what is the maximum pile length for different pile size. If no rock is encountered, 11, 15, 18 to 36.5, of course, because the bigger the pile size, the bigger the pile working load. But of course, a contractor wanted to know, what if I do encounter some rock which is IS more than 3 even at the Canny Hill area? Then we have a scenario where rock is encountered at 5 meter, 10 meter, 15 meter, etc. with different scenario of soil and of course the rock. For this case, of course, I mentioned earlier, Canny Hill Formation, I think most of the piles are formed using this only. We don't encounter any very good rock. But this is very useful for granite formation, that again, we give them what is the maximum. This is for the situation where no rock is encountered. So you can see here, we have marked certain pile. These are based on the feedback from the contractor. In this particular site, they are only mobilizing maximum where they can encounter, where they can construct the pile up to 76 meter. So if even up to 76 meter no rock, we have to redesign some of the pile groups by downgrading some of the piles to the working load where purely friction in soil. But if they encounter rock, then again, we have different scenario where we know where the pile is encountered, likely 25 to 70 meter, and what would be the rock socket required. Of course, if you have very shallow rock, you will need, for example, if you have a big pile, 1.8, if you have very shallow rock, because you have less soil, you need deeper rock socket, 3.5. If you have a very deep soil, then you only need less rock socket, 0.5 meter. So these are all the scenarios that we provide a contractor. Similarly, this is at the interface zone. You can see the interface zone also, we've given a scenario. Of course, interface zone, you can see some of the rock is higher because in this interface zone, we have assumed that it will be the sedimentary rock coupled with the granite type of soil, which is not as good as the Canny Hill interface. So only with enough SI, we can cater for this kind of a different scenario, which will ease the construction at site. So I've come to the end of my presentation. So in a nutshell, in a summary, I have only one, perhaps two, simple but often overlooked message. First, the main one, the one important is that SI is very important. I'm sure most of you have encountered certain site where the client maybe wanted you to design the foundation based on 1 borehole or 2 boreholes. And of course, I think as for me, the challenge as a consulting engineer is that we always have to convince the client that why is it beneficial to have an instrumental test file results. So I think you can see from there, for a site, even same site, different contractor, you may have different kind of results because the methodology, the construction of bore piles is different between different contractors. As I mentioned one example, some contractor may decide to use deep casing. Some contractor may use very shallow casing and rely on the stabilizing fluid. So all this will have effect to the performance of the piles. And some may decide to use polymer. Some may decide to use bentonite. And some nowadays with some newer technology, they have a mix of bentonite and polymer. All this will influence the performance of the piles. So I hope that I've illustrated the benefits of instrumental test pile results. So you see, this is my CEO, Dr. Gui, shared with me this cartoon that, of course, leading PISA, they're lucky now that it becomes a tourist attraction. But can you imagine if you're a designer there, then and somebody come and tells you that my design saves the cost of a site investigation. I think for me, I think that is not something we should save on site investigation, because there's a famous saying that you say that we have heard, some of you may have heard, you pay for soil investigation whether you carry out or not. In fact, you eventually pay more without a soil investigation. And this is in fact proven from a survey carried out by ICE, the ground board of the Institution of Civil Engineers in UK. They have published it, a simple report or publication, a very simple, call it inadequate site investigation. Some of the principal conclusion is that, in fact, most of the delay and escalating construction costs for a lot of construction sites are due to inadequate site investigation. They find the problem after the conclusion of design, and during construction, during they found out the challenges, which contributes to delay and escalating construction costs. In fact, the consequences of inadequate SI is not only severe during design and construction stage, but it may be even more serious for full life costing, in what sense that eventually maintenance costs. Imagine you are doing a road project, continuously you have not budgeted enough ground improvement. So you have to continuously go back to do maintenance. The full life costing becomes very severe. So that is basically, as I mentioned earlier, a simple message that I hope to share with all of you today. And I hope that you have benefited from my presentation today. Thank you very much.
Thank you so much, Engineer Chow. Now is the question and answer session. So I will go to the question number 1. Okay. From Ying Sim Chia. Sir, may I know what is the PLT index strength which you will consider as rock for contractor to claim under rock boring rate instead of the usual soil boring rate? Is it site specific, or you will use this value for all sites?
Okay, I assume it's Mr. Chia. I think that's a good question. A quick answer is it is site specific. It's not fixed for all type of rock. Because I want to give you an example. Let's say you in the extreme area you have granite. Granite, the uncompacted strength easily is more than 40 megapascal, and can be as high as 60 and 80 megapascal. And then on the other spectrum, when you're talking about sandstone, siltstone, most of the time, even a solid, you can get a solid rock samples in a sandstone or siltstone or schist. The UCS is less than 20, maybe 10. So in those cases, the IS will be different. That's why it has to site specific. But from my experience, normally in limestone and granite, normally it's more than 2 to 3. Whereas in Kenny Hill, in sandstone or schist, it can be as low as 1 or 1.5 or 2. And why is it very important, has to be site specific, is that, I mean, this is a bit on a contractual argument. Most of the time, there's a lot of dispute in terms of the payment for rock coring. If you don't have the data from site specific from the SI to justify a recommendation, of course, there are grounds for a dispute. The contractor, to be fair to the contractor, of course, they say that, hey, your site, all your point load index is less than 3. Why are you defining the point load index as more than 3 in my case? So that's why it's very important that you have a site-specific values. Okay, I hope I answered your question, Mr. Chia.
Okay, next question is, okay. Yes, sir, you mentioned that from previous experience, when concrete grade for your bob pile is grade 40, your shaft friction is of a certain value. How does the concrete grade of the pile affect the shaft friction, and what is the formula to calculate this?
Okay, I I think this one, I apologize if I didn't mention it clearly. In my slide, actually, when I talk about UCS of strength of 40 megapascal, I refer to the strength of the granite rock and not the concrete grade for the bore pile. So I think that one is quite straightforward. If I refer to the strength of the granite, of course, there are quite other correlation. For example, William and Pels, if I'm not mistaken, in Canadian Geotechnical Journal, they have a correlations in terms of determining the rock shaft friction based on the strength of the rock, and then they reduce it based on what is the LQD or the fracture state of it. So I think that we can relate to it. Naturally, stronger the rock, generally the friction should be higher. But having said that, you have to be careful as well in the sense that the bore pile grade don't play a major factor. I must clarify that first. But you have to be careful that you do not the concrete grade of the bore pile will have some influence on the friction capacity as well. Because you imagine if you have a very weak concrete in a very strong rock, one of them will fail first. So in this case, maybe the interface or between at the concrete grade is not strong enough to mobilize the friction. So it has some bearing. That's why sometimes you don't want to use too low concrete grade as well. It may lead to slightly lower rock friction as well. Thank you. I hope answer his question.
Okay. Next question is from Siu Kok Tong. Dear Engineer Chow, is it necessary to do point load test in every of the borehole to determine the rock strength?
I mean, I can only share my Mr. Sel. I can share from my experience. I don't for my boreholes. I normally don't do it in every boreholes. But actually, I don't see any problem doing it in every borehole as well, because actually point load test is quite cheap. The actual challenge is to whether you can do enough UCS in all boreholes, because UCS is more expensive and you wanted to correlate between the point load index with the UCS. So again, a quick answer from me is that I don't normally do point load test in every of the boreholes, but I don't see the harm in it as well, because point load index is not that expensive. So depending on how many boreholes that you actually have.
Okay, next is 6-meter core length in granite sufficient for 1.8 meter diameter board pile? Any recommendation of SI termination criteria for rock socket in board pile design? I think this is a question, because I think that is the criteria for JKR, I think.
Yeah, in JKR. I mean, I think this is a very good question. I have to be clear that that's why I wanted to share today's presentation. In normal circumstances, you're talking about 6-meter rock core length into granite, I think is sufficient as SI termination criteria. Because for normal granite formation, from my experience, you seldom have boulders, because you're worried about boulders, granite boulders before reaching the bedrock. From my experience, you seldom have any boulder the size which is bigger than 6 meters. So most of the time you call about 2 to 3 meters or 1 meter, you will punch through the boulder, then you reach the granite bedrock. In normal circumstances, I think 6 meters is enough. But what I want to share with you today is that perhaps you have to be a little bit more careful at interface zone. You see, for example, you're talking about limestone. Normal criteria for SI termination criteria in limestone, normally we're talking about 10-meter coring in cavity-free limestone would be enough. But that's why the gist of my presentation today is that if you are at interface zone, certain case, 10 meter may not be sufficient. In fact, you may have 20 meter of limestone, then thereafter you found that you have quite thick layer of soil. then only you reach granite in my first case history. So in this case, probably you may want to have 1 or 2 boreholes at interface zone that you may want to go deeper, just to be sure that you don't encounter the site which I've shared with you earlier on. Okay, that is my advice.
Okay. Next, because we have quite a lot, quite number of questions, so I just go one by one. The next one is for site with limestone. Is there any general rule of thumb on the quality of borehole you would recommend to your client? As in 1 borehole per area? That is the question, I think.
I'm afraid from my experience, we don't have a rule of thumb on the quantity of borehole. I think that I don't believe there is much guidance on that as well. So if there's any rule of thumb, I just know that normally for limestone, you expect to have more boreholes than other more straightforward site, for example, maybe Kenny Hill or granite. And the best strategy would be always to divide it into a few stages. That means you start with less borehole, and then if you find that your site have a lot of uncertainties, then you go to the next stage and try to verify the uncertainties. I'm afraid I'm not aware of any general rule of thumb on the quantity of borehole for limestone.
Next question, I think, is from Tian Xin. When you design your test pile, TP 900 and TP 1800 in case 1, what is the shaft friction and end bearing values adopted? And what is the factor of safety adopted?
Okay, for the case 1, I've shared earlier, when we assume the granite formation, we assume it's 1500. And for the soil, we assume it's based on 2N, end bearing is 4600. So, of course, maybe I'll share my screen again for this particular case. Sorry, I have to close there. So just to go through very quickly, of course, the ultimate is 1005, 4006. But I think the important value that I want to mention is that 1005 is all based on assuming IS more than 3. And subsequently, we found out that it works quite well because the IS value that we obtain for the test pile, in fact, is not more than 3. Some of them is less than, most of them less than 3. For those that are more than 3, I go back, you can see that it's not 1005, but I think it's not too bad given the situation. It's about 10% less than that. So we don't really have to downgrade the piles by a big margin. Okay, this is just to answer.
Thank you. So next will be quite a long, few questions in one from one person. So number 1 is, what is the recommended termination criteria of SI for limestone? I think you have answered earlier, isn't it? This one.
Yeah. Yep.
So number 2, in your foundation design, would you consider the pile friction above the bedrock or floaters?
Yeah. The second question is that from Mr. Lee is that I don't consider the pile friction on the floater. For the soil, of course, I would assume it's like a soil because in my approach, I do not know the extent of the floater. That means how big or wide is the floater. So the approach is that the thinking behind is that, can you imagine when you design a pile that goes through a boulder? So of course, you will not consider the boulder as a rock friction because after the boulder, it's still surrounded by soil. So we consider it as soil. That's for question number 2.
Yeah, number 3 is normally RQD in SI will reflect similar to rock strong. Could we use it to verify the rock strength, RQD, or in the SI?
Okay, my quick answer is that I would say RQD reflects more on the fracture state of the rock, not so much the strength. See, let's say you have limestone, you have granite. You may have both similar RQD, but the granite UCS may be 80, the limestone UCS may be 40. So I would not use so much the RQD. I mean, this is my opinion, I would not use the RQD to verify rock strength, but it will give me an indication, assuming it's the same rock formation, what would be the relative rock friction. Of course, the higher RQD, I would think it will give a higher rock friction.
Next is from the same person. Some engineer will justify the rock strength by use of rock color. What is your opinion?
Okay, I think nothing wrong to have an idea in the rock strength by use of the rock color. I'm guessing that Mr. Lee is referring to the degree of weathering, because when you talk about fresh granite, the rock color will be different. When you talk about weathered granite, you may have some staining of the soil or the iron. So that is in fact the degree of weathering of the rock. But the problem that I have is that this is not quantitative, this is qualitative. When it comes to construction, how do we put the numbers to the rock strength? I mean, it cannot be one day myself. I look at it a bit brownish. I decided to reduce the rock strength by half. Engineer Rafta look at the same rock. She may decided to really downgrade it by 20%. So these have become very subjective and may lead to a lot of argument. So my answer would be qualitative, yes, but not quantitative.
Okay. Next, what is the condition? In what condition you will ignore the pile rock socket length and treat pile as treat as pile on soil? In what condition you will ignore the pile rock socket length?
I think I would not ignore rock socket length if it's definitely bedrock. I think maybe Mr. Lee is referring back to floater again. Of course, if it's your pile is in floater or boulder, as I explained earlier, your pile even don't go through a boulder, but the boulder is actually surrounded by soil. So I would not use that as rock friction.
Okay, next I would jump through the question from Muhammad Azim. Is there any specific reason on the difference of PTP methodologies, that mean cartilage and bidirectional, to be have been adopted for this project? So they want to have the difference.
Okay, I think main thing is like this. In Sheikh Muhammad Azim, I've shown pictures of cartilage. Cartilage is a very traditional approach where we stack concrete blocks to test the power. I think very direct. Engineers are very confident with it. Whereas bidirectional are relatively, compared to cartilage, it's quite a newer technology, but it has been here for quite some time already. So main difference is that if you want to test big piles, it's quite impractical to stack too high. It can be very dangerous and very costly to stack very, very high dead loads. And the only practical way to test it will be bidirectional. So that's why you can see from my presentation, smaller piles, we can still use cartilage because, like I said, cartilage have been proven and tested. At least I have some comparison result between cartilage and bidirectional. In fact, for my second site, for a very small pile diameter, I just share a little bit more, is that one of the test pile was not successfully constructed using bidirectional. Because bidirectional, we need to put in the jack within the pile. So if the pile is very small diameter, it can get very congested and very difficult to concrete. So for that particular pile, in fact, the concrete for the pile was not formed properly because of the congestion of the jack, and we have to abandon that test pile. So that's why bidirectional, in a certain way, is best suited for bigger pile diameters.
Okay, I have two more questions. So I choose the from Frederick Tan. Is there any available database for correlation of shaft friction and bearing of different rock in Malaysia and their respective IS value for preliminary design purposes? You have any database?
Yeah, Frederick, unfortunately, so far as I know, we don't have yet, and unfortunately, I think I may be wrong. I believe myself and my colleagues, the ones that first started using it, and I think that is a very good suggestion, sir. I think if I can shake away my lazy bone, I think I have to collect all the ball power test results and IS value and come out with recommendations in terms of the friction. By this moment, I have not published it yet at this moment. So it's not compiled in one place, but if you search from my company's publication, I mean for myself and my colleague, we have different kind of results for granite and limestone, all published separately. That's all we have on it.
Okay, the last question from Zuharlini Tuan Haris. What is your opinion on the pre-bore jack-in pile in sandstone formation versus board pile?
Okay, I think this is again a very good question. Maybe even though it's not related to this particular presentation. Inche Zuhani, I'm not sure, sorry, Zuhalini, I'm not sure it's Inche or Tuan. Inche Zuhalini, Tuan Harif. In fact, I mean, a few years back, I've given a presentation on jack-in piles in sandstone formation versus ball pile. In certain situations, for sandstone, if you're shallow, your hard layer is shallow, that means you can use very short jack-in pile. It can be a viable alternative to ball pile, because why? The main just for your benefit is that the main difference is that for jack-in pile, the base we are very sure it can be mobilized, because the process of jacking it in and the construction process is that we don't expose the pile for a very long time. So the pile tend to be shorter for similar diameter compared to ball pile. As I've shown you earlier in my slide, ball pile, the end bearing in canyon formation or sandstone formation for that matter can be quite small. In fact, I published a paper talking about pre-bore jack-in pile in metal sedimentary formation. I think maybe about 6-7 years back in an Asian regional conference. If you need it, maybe you can drop me a message. I can share with you that as well.
Okay, I think that is the end of the question, even if we have a few more, but times is doesn't allow us to go further. So it's nearly 6 o'clock. So thank you so much, Engineer Chow, for the presentation. Very informative and very so here there is a link for download of the presentation slide. So I will like to thank to everybody. We have 274 participants for today's webinar. Thank you for your support and thank you. So our webinar will end here. Thank you so much.
Thank you, Gerald, for sharing. Thank you very much. Thank you, everyone. All the best in your projects. Bye-bye.